My name is Portia, and I'm a current sophomore in engineering physics. My MRF project for this year was to develop an experimental platform for cryogenic thermal conductivity measurements. Thermal conductivity measurement techniques are well established at room temperature, but become much more challenging at low temperatures since normal thermal transport mechanisms, specifically electron-phonon scattering, freeze. To combat this, low-temperature thermal conductivity measurements require three fundamental components to ensure accuracy: thermal isolation of the sample, highly sensitive local thermometry, and a controllable temperature gradient via joule heating. The goal of this project is to use these three components and develop a dedicated thin-film thermal conductivity measurement platform for cryogenic temperatures, particularly below 1 Kelvin. While many materials have been measured at low temperatures, there is limited data for materials below 1 Kelvin, and this project hopes to help fill in that gap. For any sample, the thermal conductivity of the substrate contributes background noise to measurements. This background noise is directly proportional to the substrate thickness, so bulk samples have a much higher background than thin films. Our chip is uniquely designed to minimize the background thermal conductivity by suspending the material to be measured on a very thin silicon nitride bridge, as you can see on the slide. This suspension ensures that the thermal conductivity of the background is less than that of the sample, which allows for more accurate measurements, especially at low temperatures. At low temperatures, it is critical that we are able to measure the local on-chip temperature. To do that, we developed highly sensitive, focused ion beam deposited carbon-platinum resistive thermometers. In the left image, we can see the small white platinum nanoparticles suspended in a black carbon matrix. Both platinum and carbon are good resistive thermometers on their own, but platinum loses sensitivity at around 10 Kelvin, and carbon thermometers are difficult to use for local microscale measurements like we need here. However, the fib-deposited carbon-platinum composite has unique conduction characteristics independent of either pure platinum or carbon that make it a sensitive thermometer at cryogenic temperatures, and it is extremely easy to pattern directly onto the sample. Since the composite is amorphous, the thermometer resistivity is extremely dependent upon the sample morphology. As you can see in the plot on the right, 3 thermometers deposited at the same ion beam current have slightly different percent changes in resistivity. While slightly variable, the sensitivity of these thermometers is still comparable to leading commercially available cryogenic thermometers, specifically ruthenium dioxide, which is also plotted. These thermometers are uniquely suited for this application because they can be patterned directly onto the suspended platforms without risk of damaging them. On the slide, you can see the thermometer deposited across 2 leads on one of the suspended platforms to measure the applied temperature gradient across the silicon nitride bridge. To get a temperature gradient across the silicon nitride bridge, as shown on the left of the slide, we can apply power to a joule heater on one of the suspended platforms and measure the change in temperature, or delta T, across the suspended silicon nitride bridge via our deposited fib thermometers. Due to the geometry and the suspension of the bridge, radiative heating effects are negligible, and we can be confident that the applied heat is mostly directed across the bridge. The plot on the right shows the change in temperature as a function of applied heater power across a bulk silicon substrate at 10 millikelvin. Since the silicon nitride bridge is both a thin film and suspended, we can expect a delta T greater than what is plotted here. We know that the thermal conductivity of a sample is a function of the applied heat, the distance between the measurement points, the area of the sample, and our measured change in temperature. Knowing the geometry of the silicon nitride suspended platforms and connecting bridge, we have developed a fully repeatable method to measure and control the applied heat, and therefore delta T, across the suspended silicon nitride bridge. This unique platform design can be used to measure the thermal conductivity of any material deposited upon the suspended bridge using standard thermal evaporation or sputtering techniques. And I'm looking forward to testing various materials on these suspended bridges in the future. I would like to thank Dr. Singh for her advisement on this MRF project, and Dr. Zink from Denver University for providing several of the thermal isolation platforms. Thank you.